Thank you very much. Can you see my presentation?
Yes.
Great. Well, first of all, let me thank the organizer for inviting me. I will try today to give an idea of something which is very, in my opinion, very interesting and has been driving my research for the last years. And I want to start with a little game I do all the time. So some of you have seen this before, a previous talk I may have given, but I like it very much to make a point. So about paradigm shifts. So this is what is called a dovetail, and you know, you find it all over the place in your house, in every possible thing. It's basically something to constrain 5 degrees of freedom and leave one open, so that you can assemble things easily, and then you fix the last degrees of freedom. The point is, and the question that I often use with this game. So if you have seen it, you know the answer. But of course, if I give you this and I ask you, can these two pieces move? Now you have to think about it, and you say, okay, you know, if I ask you, it's probably there's something behind it. But a number of people will say, impulsively at least, if they would say, oh, this can never be disassembled. Well, unfortunately, that's definitely not the case, because this can move like this. And then I can ask you, okay, are there other solutions? Of course, there is a symmetric solution with 90 degrees rotation, but are there more? And well, it turns out that there are infinite solutions. And just to give you another one, this would be another solution that you may have. Why am I showing you this? Well, I'm showing you this because very often you are used to think in a certain pattern, and you do not see other ways to looking at things in a different way. And here specifically, you look at the outside without actually considering that at least there are a lot of possibility behind the things you actually see. So I will try today to show you a new way of looking at things and the model physics in general that is, I think, has completely changed my way of looking at the various things I'm doing with. And this will not surprise some of the people who know me, Porter-Miltonian system theory. And actually I have some new results, which I developed in my ERC on a very complicated physics model in these ways, which give insight that was never given before, in my opinion. So robotics is the science of integration and embodiment of technology in the physical world, and certainly in soft robotics, you need to understand, as it was just explained in the introduction, how things work, you know, with deformable materials, possible fluids, and all these kind of things. So I want to present this methodology which actually can be applied to any kind of physical systems. And I am pretty sure that in the future, this will give a lot of insight in specific soft robotics applications. I will give an introduction first, then introduce the basic concept. I mean, wouldn't need much more time than, of course, it's available in a session like this. So I really have been trying to find a way to be useful, this talk, to give you an insight and a feeling of it, and at the end give you down the complex results. Of course, I cannot go in details, but just to convince you, at least to try to convince you that this stuff is really interesting. So starting introduction, I would like to cite Aristotle. And he said that in all things of nature, there is something of the marvelous. Of course, people, especially people working in robotics, are probably fascinated by nature and the fact that, you know, animals and humans can move around, behave, and understand how to interact with the physical world. And one of the most amazing things in nature, in my opinion, are birds. And already Leonardo da Vinci, you know, 500 years ago was fascinated by this, as was also reported in the Codice sul volo degli uccelli, which can be found in the library of Turin. And we have actually a bird, a pretty amazing robotic bird, you may have seen before, which is pretty unique because it can go up to 80 kilometers an hour speeds, has a real weight, the same weight as a real equivalent falcon, same payloads, same flight per frequency, and it can, and this is really unique, fly in 5-4 wind. There are a lot of flapping birds, but there is no one else I know, at least that can fly this. You know, Festo has done amazing things, but in that wind, it would not be able to fly. This has had a number of recognition. You may have seen it on the robotics in the magazine, and we got the European Tech Transfer Award for the enterprise, which is now exploiting this in the airport, for example. And we do not really understand the details. You know, this was reached to this way, just also we'll try and error somehow. And some ideas of how that works is based on something which is called fluid dynamics reverse von Karman sheet generation, which basically create, as you can see here on the bottom left, some vortices which are crossed and create the jets in the midstream that basically create propulsion for the flapping. But this is just one thing, and if you go to 3D, things are not as clear. So the goal of the ERC I had the fortune to get was to really try to understand this and really use the physics modeling methodology I will try to introduce in order to achieve that. If you want to know more about the project, there is just a new publication, an annual review and control, which gives an overview of the whole idea of the project and various aspects, and which is titled Decoding and Realizing Flapping Flight with Porto-Hamiltonian System Theory. This is the team I have the fortune to lead, and really is my dream team of very talented young fellows. And you can find information on the project at portwings.eu. And it's basically the pillars are the fundamentals, which I will talk mostly about today. The numerics, which is a very exciting new things I will not talk about today, but we are really reaching something really cool. Some things on smart designs that I will not talk at all about, smart materials and experimental fluid dynamics. And as I said, these will be the things I will concentrate about today. And it all started after 1 year of digging into the math and the theory of physics of fluid dynamics, which brought to these two first articles, which are now published on the Journal of Geometry and Physics, which were actually put on Arvix when they were in review. They were immediately accepted. And in the meantime, we actually were invited from the editor-in-chief of the Physics of Fluid Journal, which is, you know, the top journal of fluid dynamics, for an invited paper which is now published, which actually bring all the ideas to the dissipative case, to Navier-Stokes, total Navier-Stokes equations. And as I said, there is this general paper you may be interested to have a look at. So the idea is to model all the physics of the bird meanwhile it's flying. And of course, you know, if you think about the connection of the wings, well, that's, let's say, pretty standard robotics in the fact that, you know, rigid body connections of the rigid parts. And we used Lie groups for that. These are especially Euclidean groups. I will get to that in a moment. But that's, you know, pretty standard robotics, I would say. The problem, of course, realize when the wings are deformable, when they are soft, because the wings, if you make the wings rigid, it would not fly. It has been tried, does not fly. So the wings, the fact that the wings deform, meanwhile fly, they have a twist and a deformation, it's absolutely essential for the flight. And the point is that, you know, how do you model that? And even more complicated, how do you model the interaction between the wings and the fluid around it? That's complicated physics. And that's the goal we want to achieve. What you see here are Navier-Stokes equation in an ugly format, which is the normal way. And we wanted to understand this much deeper. And we got to some new mathematics that actually showed some very, very interesting insights. So the conceptual challenges are to understand of the project, the geometrical, possibly curve, coordinate free weight of the fundamentals of open ideal fluids. The Euler equations are basically Navier-Stokes without the dissipating terms. But normally these PDEs, you know, always have fixed boundary condition. If you have a wing flapping in the fluid, you don't have fixed boundary condition because the wings are moving all the time. It's deforming. So you have two PDEs basically which are interacting in real time. And this, as I said, brought to these publications. Then we extended this to a compositional way to be able to also model any advection, because in a fluid, of course, if you have, for example, heat generation, thermodynamics, and you get to what are called Fourier-Navier-Stokes equations, and other things, compressibility of the fluid, which we can handle very elegantly, then you need to talk about advection. That was the second paper. Then including the shear viscosity, bulk and shear viscosity. So bulk viscosity is basically the dissipation of energy when the fluid is compressed or dilated. and shear viscosity when the molecules shear from on each other. And then the next big challenge, which actually we have solved already, I'm very excited about, we haven't published, we have finished finalizing the paper, is really to handle the complete general case of variance boundary, which will allow us to model, you know, flapping wings in a fluid totally. And the last, so this is really, we are finalizing the paper right now, and the last is really to translate all this, which is purely in algebra and continuous time, to the discrete case, because you want, of course, to discretize this equation, to simulate, and then to do learning, for example, on this, to understand the fluids and learn how the birds can move in this fluid. And I am extremely excited because this would basically be able to couple discretize PDEs together with, so partial differential equations together with ordinary differential equation or algebraic differential equations. And we are close to something really exciting. This weekend I couldn't sleep from how excited I was about some new things. So it's really promising way of proceeding. Okay, so let me give you an introduction on what is the core idea behind all these things. It all starts from energy. And you'd recognize this guy, probably one of the most well-known scientists ever, Albert Einstein, who actually said in a statement which you can read totally, but basically said, you know, all theories in physics will be passed, even relativity, but one thing will never be passed, that thermodynamics. Why? Because energy and power are the basis of the glue of physics, basically. Okay. And all domains use this. So you can use it to multiphysical domains to handle that. And we described energy and power to talk about all these things. And the way energy and power transfers is actually the basis of interaction in all possible physical domains. Okay, so this is the core. Now, this guy that you may recognize was Hamilton, and you know, Hamiltonian theory is the basis of physics as well, but it's very restricted. And I want to compare it with what I call the Port-Hamiltonian's way of doing things, which is basically what I call the physics Lego, because you can really interconnect things together, as I said, you know, the formable wings to the fluids, or the wings to the body, etc., to control even, because it's really, all the boundaries are open, is an open interconnection subsystem. So Hamilton theory is mostly based on a reduction, which is called the Poisson structure. And instead, Port-Hamiltonian system theory is another structure, which is called the Stokes structure. Stokes come from the Stokes theorem. Hamiltonian theory is usually top-down. You put the whole system together and you try to describe it with one single equation. Instead, the Port-Hamiltonian system theory approach try to decompose the system in a various part, and the various parts which are energetically. So you try to define a graph which is not the physical graph, but is the energetical decomposition of the system, to understand how the physics and the interaction based on energy, as I said, is working. Hamiltonian theory is closed. So, you know, once you have a system, that's it. You cannot do anything with it. I mean, you can analyze that system. Instead, Port-Hamiltonian system, this is completely open. You have ports, which I will introduce in a second, which will allow to attach the system to something else, and then being able to attach it as a Lego to another part of the system. And as I said, you know, Port-Hamiltonian system theory is completely open. You can write equations with the boundary open, and then you can use that boundary to click it to another physical system. And Port-Hamiltonian system theory also allows, without any problem, dissipation, or better, irreversible flow of energy to heat, for example, to entropy, which is something, you know, Hamiltonian system usually you're not able to model dissipation. That's no problem at all with Port-Hamiltonian system theory. So the basic of the whole theory is based on duality. Duality is a concept, of course, that, you know, in control, in system theory is well known, but here it really pops up even stronger. And the core idea is that energy and power are scalar, you know, are just scalar value function of time. So they have no geometry. They are not depending on coordinates. But then what you want to do is you want to describe, because, and this is, for example, you have a subsystem A and the subsystem B, which want to interact with each other. And this is the port I'm actually introducing. And these two variables are things which are shared between these two systems, and they do have a geometry, okay? These are called efforts and flow. And these are elements, are things which are in duality. I will give you an example that you will understand what I mean. So a power bond is really the embodiment of the tensor duality that the system or subsystem A and B share in order to describe the way they interact with each other. So once again, geometrically speaking, an effort is, so a flow is a vector space. It can be an infinite dimensional vector space, as I will show in PDEs. And an effort is nothing else than the dual of that. And what is the dual? Well, mathematically is defined as basically the linear map that maps the flow, the vector space you originated with, to a real number. And that real number is power. So you see, you have power is a scalar, but then you have the flows are a vector space and efforts are the dual of that vector space in a very general sense, as you will see. And once you pair them in a natural way without any need of any other structure, what you result is the power that is basically transfer from A to B. You see the half arrow indicates the positive direction of power. And you can talk about causality, but this is irrelevant. So let me skip on that. Examples are in electrical domain flows, well as that scalar, that's no geometry, also at the effort and flow values, so current and voltage on velocity and forces. But when you go, for example, to robotics, rotational mechanics or rigid body mechanics, you have this duality, which is, the twist and wrenches, the angular velocity and the torques. And it turns out, and in continuous mechanics, you need tensor valued M forms, I will introduce in a moment. But it turns out that when you go to the geometry case, the system A and the system B, as I introduced, are different systems. How can you define something common between the two? Well, you need an Esperanto to be described this vector space and this dual of vector space. Well, it turns out that there is a mathematical way of doing that, which is based on what are called Lie groups, which I definitely don't have the time to talk about, and especially Lie algebra. So basically, the efforts and the flow will be Lie algebra's element, which is a vector space with other properties, and the dual of that. So, and then the whole theory is built around this. First, the concept of power ports. Power ports is also embodiment of what is called Heaviside principle. Basically, that says that energy cannot disappear in one point and appear in another point, but needs to transfer the space in between. And what you see here is the continuity of energy is by saying that the density of energy times derivative of that is equal basically to the flux which dissipate through space to that point and the generation or dissipation in that point. And then you have concepts like store of energy, like elastic, inertially, magnetically, chemically, entropy, whatever, and dissipation, that in fluid dynamics, for example, is embodied in bulk and shear viscosity, as I mentioned before. And then how the energy transferred and distributed. In soft robotics, of course, if you have something moving, the energy that you generate from your energy source within your soft robots will then be transferred to the environment around it, and the environment will interact and will have effect on the soft robot. So it's how the energy transfer from the various system is this point. All this is basically the basic ideas. In the meantime, this is all we should write a new one. But the all ideas can be found in this book. And basically, any physical system can be written with this graphical structure. Well, basically, the yellow things are the ports. So basically, think about the water pipes, where water is energy. And this can go through these pipes. The sea is basically a balloon in which you can store water. Okay, it's a tank, it's an energy tank, if you wish. And then you have, this is a power continuous thing. So there is no water here or energy that can be stored here. So if something comes here in, it has to go this way or some other ways. This is just the topology of how the energy is transferred to the various subparts. And when you talk about dissipation, which of course dissipation of energy goes against the first principle of thermodynamics, is actually irreversible transformation of energy to heat. This is basically indicated with this R element. So let's talk about to understand what it's all about. So as I said, in a finite dimensional case, the flow and the effort are basically functions of t is time and v is a vector space, whatever that is. Okay, and effort is a function of from time to vector space. So you can imagine then I can apply a vector space to a dual vector space, that I get a real number. And that would be the power as a function of time, because effort and flows are function of times. And this, basically by this construct, you can model all finite dimensional systems. To give an example, suppose you have an amplifier, and an amplifier is connected to a motor. Okay, an amplifier, basically, you can define the port like the voltage and the current, okay? And the product of these two things will basically be the power that the amplifier gives to the motor. Well, the motor will be attached to a joint which connects two bodies. Well, and then it will generate a torque, and there will be an angular velocity, okay? And the product of these two is again power. That's the power that goes from the motor to the joint. Could be negative, right? Could come back to the motor. But then if you want to connect and talk about the robotic side of it, of course, things get a bit more complicated. You get a multi-bond, what is called a multi-bond. And then you have the geometry you need are the twists and wrenches, which are elements, as I said, of Lie groups and this dual, which basically shows how the joint is connected to body one and to connected to body two. And then you see that indeed, these ports can be generalized from, electrical, mechanical domain to multi-body dynamics. The problem starts when you want to go to an infinite dimensional case, because then you're talking about things which are distributed. How do you handle this? Well, then you need to talk about the domain on which these things live, okay? So you need to talk about a manifold, indicated here as M, which is, think about it, a surface. So for example, the manifold of the fluid will be the space in which the fluid moves, which could be curved. If you talk about atmospheric studies around the Earth, that could be a sphere, the manifold. And then the boundary. In the case of the Earth, there is no boundary. But if you want to really talk about, for example, the wing, the surface of the wing in a fluid, that would be the boundary between the manifold where the fluid moves and the manifold when the continuous mechanic of the wing deforms. And we want to be able to use a language, we want to be able to do it in all dimension, coordinate free, applicable to all physical domain, and possibly to curved spaces. So because if you do it this way, you really understand the physics. As unfortunately in engineering, I could give you a number of examples. We are raped, I say, as engineers, when we are educated, we are raped with coordinates. Because then we think that certain things are the way we see them, but they are not, because they are depending on the choice of coordinates you do. So coordinate free is very important. And in order to handle PDEs in this way, you need what is called exterior calculus. Of course, I want to give you a primer in exterior calculus, and some of you know it, but I think that otherwise you wouldn't understand how to explain the things that I want to come to. The basic object of exterior calculus are called differential forms. And basically a K form, and they can be of varied degrees, are completely antisymmetric K linear fields. So basically is a field, so it's defined on a manifold. And so, for example, if this is a manifold, in each point you have basically a linear operator. You see, it's a field, is function of where it is, the X, and the time it is measured or used. Okay, and you feed to it K, that's why it's a K form, K element of K vectors attached to the points where the field is, okay? And this returns a scalar number. That's what the K form is, no more, no less. And the thing which is important for K forms is basically K forms measure volume of a K dimensional subspace. So in other words, the natural way to measure, for example, a length of the line is to integrate the one form along this line of a surface is integrated two forms on the surface and three forms to integrate volumes, etc., etc. But it's a more general way to measure things which are related to a line, to a two-dimensional, three-dimensional, etc. That's what you need this stuff for. And then you have three basic operations that works on this algebra. The first one is what is called the wedge product. It is something that basically takes two forms, a K and an L form, and it returns a K plus L form. It sums the dimension, okay? And another one is the D differential operator. This basically take if you wish, is the generalization of gradient divergence, rotational, and all these kind of things in vector calculus. And what comes up to this generalization of Stokes theorem, which basically you see, if you have a form which you take the d, so increase the value. So suppose that there is a 2 form on a surface. If you take the d, it becomes a 3 forms. So this would be the integral on a volume. The integral on the volume would be equal to the integral of the 2 forms, which was a 2 forms, on the boundary of the volume. Okay, so you see it's generalization of things that you have seen in vector calculus. And the last important thing is which gives the metric property, these are only topological properties, is what it's called the Hodge star operator, which basically can map a form of k forms on the n minus k form. So if you have, for example, a 1 form in a 3-dimensional domain, it will map it to a two forms. And this is used to create basically a Hilbert product, so an inner product between these forms, which is needed to calculate energy in the distributed way, for example. I mean, this is it seems very complicated. Let me try to give you an insight. And so in a distributed space, so if you want to measure a volume, as I said, you would measure the power through a volume. We would measure, for example, an n form. If you want to measure the power through a surface, then you would measure an n minus 1 form. And this can be expressed as effort and flow. So if you have a port, suppose you have the wing and the fluid, and you want to talk about the power which is exchanged between the wing and the fluid, well, the wing surface is a 2-dimensional surface, okay? So you need to integrate the 2 form, okay? And the efforts and flows will then be 2 forms, such that the sum of their dimension will give you 2, okay? And it will be, for example, pressure, which is a scalar, okay? And something else, which is a 2 form, which you can then pair, it becomes 2, you can integrate, and that will be the port, the power exchange between the fluid and the wing. So an example, let's talk about the energy again. So the energy densities, if in a 3-dimensional space, n is 3, okay, you need to integrate it. And energy is function of the state, the physical state you want to describe, which is XL, which is again a form in this case. And of course, the total energy in a certain domain is nothing else than the integral of the density of that domain. And then once you want to do what is the time derivative of the domain you describe, for example, a subpart of the fluid you want to describe, then you can describe it like this, which is like kind of partial derivative, if you wish, which is actually the variational derivative of this field, wedge the time change of the field itself. And then you see immediately that indeed the dimensions are such that again, the dimension is n, so you can integrate the change in energy within the volume. And then continuity also tells you that, you know, the change in energy within the volume is equal to, you can show by using Stokes theorem, the energy flux through the boundary of that volume, plus the energy which is either introduced or dissipated within the volume, which could be, for example, heat source or other things, or coupling to other physical domains. And if you combine these 2 things, okay, then you basically have the whole description of how energy transfers from the various domains, and these are basically the ports. So this is the port, are all ports, and if you try to make graphically this to understand it in ports, this is basically the picture you would get. You have here, you see a pairing between the Hamiltonian difference and the change in state. This is a port that basically connects the interconnection to the storage of energy, which is the Hamiltonian. Then you have the power which is flowing from within the domain, could be dissipation, for example, in the fluid. And then you have the power which is flowing from the boundary of the domain. Okay, so this is, I hope I give you an intuition of these ideas. And to very briefly going to fluids, it turns out that this is not even enough for fluids. What we realize, and that was a really aha moment, that you need something which is even a step further. Differential forms, as I introduced, give you scalar values. Instead, what we need are what are called tensor value differential forms, which are basically needed to be able to model shear stress in fluids. And the reason for that is because, well, I will come to that in a moment. So we want to describe open boundary of the fluid and not closed like this, but you know, the particles can go inside and outside the boundary. And it turns out, Navier-Stokes can be written in this way. It's not important what is written in here, but for those of you who may understand, the first one is basically momentum equation, mass continuity. This is a stress, the stress tensor composed of bulk and shear viscosity, as I said, and this is the equation relating to the energy, which in this case we consider a barotropic case, so basically no entropy dynamics. And if you want to describe it, but the way it is described that you lose a lot of information. And instead, the way we described it is we first map the motion of the particles in the fluid as a covector. So by using the metric space in which we are working on, which is the Riemann metric, in Euclidean space would be the Euclidean space. Then we define rho is basically the density of the fluid. We can define the odd, you remember, it goes to n minus k. So if rho is a scalar, which is the density of the fluid, mu would be a top form, the n-dimensional form which you can integrate, and whose integral will give you basically the mass of the volume you want to measure. And this is what we need for describing stress. So this is actually what is called a vector value n minus 1 form. So what is this? Well, basically, if you have a volume, take a ship, and a ship in the sea, okay, the total force, if you wish, the wrench of the ship is basically the integral of all the force of the molecule of water around it. So you have to integrate it, okay? Integrate basically on a surface, so you need an n minus 1 form, a 2 form in case of a ship. And in each point, you will need a vector, which is the force. So it's a force value, 2 forms that you need to do. This is why you need this stuff. And well, it turns out that you cannot actually, in curved space, you can integrate, as I said, but you can always integrate power. This was another insight, which is pretty deep, and I don't have the time unless you have a question. And we found out we need a new pair, which is, we indicated something we introduced, the dot wedge pairing, which is able to describe a proper pairing for fluidodynamics. And we need something, a generalization, what's the divergence to go from basically to handle stress, which uses what is called the exterior covariant derivative in these settings, which is a mix of topological parts, as I said, of the D and a covariant derivative, which is something more geometrical, but it's basically is an operator which generalizes the divergence in these settings. And something which also relates the rate of strain, which is, once you deform a fluid in motion, this is true for any kind of soft material, basically the Lie derivative of the matrix which measure the space itself, is fundamental interpretation, gave a fundamental interpretation in order to rewrite this equation in a setting that I don't expect absolutely you to understand this. But basically, these are the equation, the Navier-Stokes equation in these settings, which describe in a completely geometric, coordinate invariant, dimension independent, open way what we're talking about. And then we did some steps I will skip because of time, and I think this becomes otherwise too technical. If there are questions, I can go back to that. We were able to basically model this completely in port and define the ports, which then brought, these are some extra insight I will skip. Just let me get to the core, to this kind of model that you see as the same structure as before, where we have an energy function, which is the energy stored in the fluid, kinetic energy of the fluid, and potential energy. It could be, if you have a compressible fluid, would be, the elasticity of your fluid, but you could also have other kind of energy stored. And the most important things, we are able to model bulk dissipation and shear dissipation. This was the big contribution of the paper on the physics of fluids, which gave a completely new insight on how to tackle. And by doing that, we actually have got also insight on generalizing this theory to possibly non-Newtonian fluids, to even more general situation. So furthermore, we handled in the paper that I didn't talk about it at all, an interpretation of Laplacian operating in curved spaces, which was very insightful. And we give hints on how to extend this to what are called Fourier-Navier-Stokes equations that basically modeled also the generation of heat due to stress in the fluid, and therefore generation of entropy and the diffusion of entropy through the fluid or transport and advection of entropy through the fluid. So the next step we want to achieve is varying boundary. That has been solved, as I said, and novel symplectic mimetic discretization methods to step in one go from these forms to discrete methods to integrate. And we are close to, as I said, to a very big breakthrough, and I'm very excited about it. So I want to conclude just by showing video I've shown many times. Some of you have seen it again and again, but
working in aviation,
I think it's a pretty cool thing to see about the bird, and then I will
can be a
conclude.
great nuisance. Birds spread diseases, pick up waste, and pollute the surroundings. Nothing, however, tops the risk of bird strikes in aviation. Clear Flight Solutions has the answer to your problems. The Rollbird. The Rollbird is an environmentally friendly solution for all your bird-related problems. It is a flapping wing robotic bird that not only looks like a bird of prey, but also flies like one. We have many years of experience in unmanned aviation and bird control. Our certified pilots are experts in flying our Rollbirds. As safety is paramount, our Rollbirds are equipped with state-of-the-art autopilots, GPS, and geofence systems. We make sure that the pilot in command is always in control. The instinctual behavior of birds when confronted with a predator is flocking together for maximum safety. By flying around the flock, the pilot can remove the birds lastingly in the direction of choice. Shortly after this, birds will start to recognize the area as a territory of prey, will start avoiding it. By mimicking nature, Clear Flight Solutions creates a unique bird control system that birds will never get used to. We make sure your skies stay clear.
And I want to conclude this citation. Albert Einstein said, true knowledge comes with deep understanding of a topic and its inner workings. And that's why if you want to build robots that really do like this, and our goal is to make a robot that can perch, can take off, can land, can do basically all things that in nature happen, you really need to understand how things work. Thanks a lot for listening.
Thanks a lot, Stefano, for this interesting talk. Are there any questions from the audience? Let's see, Alessandro has a question. Go ahead.
Hello, can you hear me?
Yes, Alex.
Yes. Thanks, Stefano, for your presentation. Every time I hear your presentation, I learn something more, but my understanding is not yet so deep as Albert Einstein is suggesting to have. So I have one very simple question and one more philosophical. So the first one is, I've been working on a robot with flexible link for a while, and the problem of varying boundary condition for whatever model you use for a flexible link, Euler beam or Timoshenko, whatever, is very critical. It always bored me. So for simple planar structure, for instance, we built a two-link arm with the first link rigid and the second flexible, and there the boundary conditions were not a problem. But if you have already two flexible links, and so for the second link, the inertia seen from at the base is changing, or vice versa, and this brings a number of issues from the modeling point of view. So I was very curious about this numerical solution that you give. I understand that you can go only numerical, but I would like to have some clue about this issue in this particular case. I mean, a very simple case.
Yeah, well, you touched the crack, Alessandro, we say, because the issue is from a conceptual point of view, in this, the way I presented very quickly, of course, I don't understand that anybody would grasp the details, but you can describe interconnections perfectly. There is no discussions. You can basically, if you have multiple links which you interconnect, you can interconnect the boundary condition between each other. And if you have an open boundary condition you want to use for control, for example, and the whole PD interconnection can be described, no problem whatsoever. If you want then to do discretization because you really want to implement control, well, it turns out that I think we found a way to do that in a completely general case that you will never have problem with boundary conditions. Well, I would dare to say, I don't know if you know the $1,000 questions on fluid dynamics. Yeah. Well, that may be a way to solve it, because by means of, if you can generalize this concept, you could basically, it's like saying that you can it's a way to prove solution of any PDEs, because if you can discretize in a certain way with a certain causality, etc., you're able to tackle it. So answer to your question is, with this methodology, the problems should be absolutely solved. And I hope that I will give you a convincing answer in the paper we will be writing on discretization.
Okay.
And you had also a philosophical question there.
If I may, I don't know if there are other questions.
So, but boundary, indeed, I mean, sorry, just an addition. That's why it's so exciting for me, this stuff, because, I've been working not in PDs for a while, and now I stepped over to PDs where, the biggest problem is exactly what you mentioned. And here is a no problem in this setting. So it is very powerful because it really shows that boundary conditions are not a problem, basically.
I look forward to it. So my philosophical question, if I may, very quick, is, so you mentioned at one point the need of continuity of flow. So how does this Porter-Hamiltonian continuity of energy flow from...
energy flow, yeah.
So how does this fit? I mean, we learned that classical physics or Hamiltonian physics is simply wrong in 95% of the cases. This is what modern physics says. So how does this continuity and formally
quantum mechanics
into the quantum mechanics probabilistic setting? And
well, it turns out I'm working on that with a theoretical physicist at the moment. So we are exactly trying to bring Porter-Hamiltonian system theory to quantum mechanics with Friedrich Schuller, who is a very good theoretical physicist, which I managed to bring to Twente. Well, as Einstein said, that Einstein didn't believe in, was kept, even if he was the ground, one of the, he got the Nobel Prize on something in quantum, Albert Einstein, the electrovoltaic process, but he was very pessimistic. But the continuity of energy is still valid also in quantum mechanics. In quantum mechanics, I mean, it is the uncertainty that plays a role, and the fluctuation and all these kind of things. You get a statistical situation, but there is no you can informations. You have entanglement that you have information basically. That of states which are entangled, and at a certain point you may have transformation of information without passing the space in between. But it's something which does not go against the energy continuity that I mentioned. So that's why Einstein also was saying, all physics will be overthrown, but thermodynamics will not. These things will stay. And that's exactly the point. So, and it's very exciting because quantum mechanics has a lot of different other problems, because one of the core problem in quantum mechanics is, that in classical mechanics, in system theory, you basically, if you have two systems, you interconnect two systems, okay? You basically take the cross product of the states. You have a vector, say, the system with 4 states, another system with 5 states, then you have 9 states. The dimension of the system is 9 then, okay? Well, in quantum mechanics, if you interconnect 2 states, you have a tensor product of the states. So if one is 5, if one is what I said 4, okay, you have 20 states, okay? And that is what actually rises the entanglement in quantum mechanics come from it, basically. So it's completely different, but it does not against energy transfer.
Okay, thanks.
Are there any other questions from the audience? We still have some time left.
So I can maybe jump in. I have a lot of questions, but I will stick to a very high level one, also a bit playing the devil advocate. So as you know, Stefano, I'm very much in favor of theoretical analysis and things, but if we go back to the application that motivated your work, which is the BERT. So the BERT already works pretty well right now. And now you have this theory. I mean, you are developing this theory. Do you foresee some improvement in the performance by using this theory?
Well, that's...
If yes, which one?
Yeah, well, that's the driving why we are doing this. I want to understand physics because I want to use it. You know, there is a nice way of saying this, you know, physics predicts the future, engineers make it. And I want to understand the physics to make the future. So, and what I look, the way the bird now flies is symmetric. For example, it flaps both wings, and in the tail, you know, basically can steer. So the tail has a differential mode that can steer. And the video is not autonomous, but the bird can be completely autonomous. That's not a problem. What I want to understand is, you know, that's not the way birds turn most of the time. You know, the birds, they asymmetrically flap. You know, they do funny things with the wings. If they want to perch or to stop, the motion, it's much bigger than, you know, flexible wings that flap up and down, in which you can basically change the speed. That's the way we do it, okay? And then steer by the tail. So what we want to do is, once we discretize it, we are also working on learning, on kind of AI kind of things. We want to basically use the numerics. I mean, the physics is too complicated to be able to do control in the standard way, right? So what you want to do is looking at two things. For example, model reduction. Once you have this discrete model, we want to do model reduction. And there are very cool ideas we are working on to do model reduction for these PDEs and learning. And then but you can only do this if you understand the process of interaction between the fluids and the wings, and you're able to model it in the physical way, because otherwise, you know, you model half of the physics, and it's a bidirectional exchange, because the wings deform because of the fluid and the inertial property of the deformation. So you cannot get around with a simple model. You need to understand the interconnection and physical interaction between the two.
Very cool. Thank you.
I don't know if there are any other questions from the audience. Else I still have a few questions. I see Enrico has a question. Go ahead.
Hi, thanks, Stefano, for this amazing, inspiring presentation. Just had a question about an example of robotics. So we've seen your prototype of bird. You know how you explained how the wing interacts with the flow with the air. I'm thinking, what if we had like a robot interacting with rigid objects, where we have, for example, sudden contacts with the stiff material, or, obstacles? What kind of problems would you foresee in that case, and how do you think your theory would apply?
Yeah, thank you very much, Enrico, for the comments and the questions. You can easily handle it. So we've been working on locomotion in the past, for example, and basically the idea, impact. It's all about impact, right? So if, for example, you have two mechanical parts that hit each other, I mean, the physics is not that the energy disappears, right? What happens is that when they will touch, there will be a deformation, a compenetration of the deformation of the two objects, okay, because they are continuous media anyhow, right? But the dynamics will be so fast, right, that you do not want to model the dynamics very often. And then therefore you want to basically do a projection of your state to basically say, in one shot, in one time, in event, the energy decreased and that is lost in impact. But it's a simplification. Now, you can, in this theory that I presented, you can do both. You can do the real continuous modeling of the deformation. That's no problem. Or you can, and actually we did it geometrically very elegantly, you can calculate the projection of the state and say, okay, I want to contract these times of compression, for example, to an instant. And therefore you would have a projection operator of the states to the post-impact situation. So to give you an answer, there is no problem whatsoever. This theory is absolutely able to model also these kind of situations.
Thank you.
Any other questions? I don't see anything. So I still have one small question, Stefano. So the nice thing about port Hamiltonian models is that they lend themselves for energy-based control quite nicely, right? Can you comment a bit on how you would implement this framework for energy? Do the same techniques still apply for what we use to rigid robotics, or is there some kind of new flavor?
Thank you very much, Brandon, for the question. As you know, I introduced many years ago the concept of energy tanks in controls, which is now used by a number of people. And this is exactly what the insight that this model gives you, because I think if something I've formally proven actually, so it's a theorem, is that if you have a robot, in this context, you can see a robot as being something with two ports. One port is the port that interacts with the world, so to speak, like impact or things we were discussing before, and the control port. I have proven that if you want to ensure that the system, one is interacting via the interaction port with the environment would be stable, it's absolutely necessary that controller would be passive by itself, okay? What does that mean? It means that, I mean, if you have interaction, you'd never know the worlds you're interacting with by definition, right? If I shake your hand, I don't have a PDEs that describes the way you are, right? So I need to behave in a way that ensures that, we will not start shaking, okay? Why is that? Well, it is done because the control that we intrinsically have actually has that property. So what I'm trying to say is this is not only useful for modeling, but because if you want to do interaction in the physical world, which is, in my opinion, what robotics is all about nowadays, okay, you need also to do control in a different way. And the best way, which at least the way I think is best, is the controller should also have this structure, this physical equivalent structure, as Neville Hogan introduced for impedance control, for example, in the 50s, I think. And this is the reason, because once you interact with the system, then you know that you will have a certain dynamics which is physical-like, okay? And therefore, you can define a controller, which of course will be done digitally, but this controller will have certain energetical properties which will give a good behavior once the control system will interact with an unknown environment. And this is actually, as I said, it's a theorem. I can give you the reference where it has been published. And I've proven that formally. It's very easy to prove, by the way.
Just post it in the chat.
Yes, I'll do that. Yeah.
Okay.